Today we're going to start our unit on repetitive motion. This unit's focus is going to be on sound waves and light waves and a lot of cool stuff that goes along with that. But we want to start simply. We want to look at objects like a pendulum that have motion that repeats itself in a regular and predictable manner. So let's start out with the most important terms of the unit, and they are the terms period and frequency. We got to make sure we understand what both of these tell us about our repetitive motion. So period refers to the time it takes for one complete cycle. So here is an ECG I took using my Apple Watch. And if I wanted to figure out what is the period of my heartbeat when I took this ECG, I easily could just pick a spot on the graph, go one heartbeat in, and see how much time has elapsed. This will not be the most accurate way of getting the period because such a short amount of time, we're prone to make some judgment errors. It's always better to take a larger sample. The other thing is the heartbeat might not be perfectly repetitive. There might be a little change in terms of the way it beats from beat to beat. So an average would work out better. So I start at my original spot, I call that 0. Instead of doing just one beat, I should do multiple beats. The more I do, the better my results will become. You don't want to do so many that it becomes cumbersome, but maybe 7, 8, 9, 10 cycles would be great for this experiment. So what you do is you look at what time you started, what time did you finish, and you get the change in time. To find the period, you take that change in time and divide by the number of cycles, in this case, 7. Notice that period goes by capital T, which is measured in seconds. And notice that you could pick any number of cycles that you want. A larger number tends to give you a more accurate result. And again, when you get your answer, it's measured in seconds. That is what we mean by period. Frequency, on the other hand, is the reciprocal of that. Frequency refers to how many cycles there are in a given amount of time. So you'd reverse it. Frequency, we have 7 cycles in a certain time that went by. We would then divide these two, and it would tell us how many cycles there were per second. Sometimes you'll multiply that by 60 to get cycles per minute. So in the medical field, they usually care about how many beats per minute there are. But that's not the standard. The standard is cycles per second, and that is usually referred to by the unit hertz. Okay? So period and frequency. Time over cycles, cycles over time. Okay, so for something like a hummingbird where you look at it and it looks like the wings are just a blur, it's because it's beating its wings with a very high frequency. When we watch it in slow motion, we can see that. And studies have shown that they can reach frequencies of 70 hertz. So how do you quickly turn that into a time for one cycle? That is the period of oscillation. Well, I mentioned it a moment ago that period and frequency are reciprocals of each other. So you would just take this frequency and find its reciprocal, turn it into a decimal, and that will tell us how long one beating of the wings actually takes. Okay, so when we look at music later on, we're going to be looking at the vibration of some things like guitar strings, and we might be interested in how many times they're oscillating per second, because that's going to determine the sound that we hear. The sound is predicated upon the number of oscillations it makes per second. Okay, so most times we're going to be looking at it graphically. It makes it easier to find period and frequency. So if we have a curve that looks like this, we can use the curve to find both. So again, start at 0. Go 1 complete cycle. So that means you end up right where you started. That's usually not going to give you an accurate reading. So do as many as you can do practically. So once again, 7 seems to be the magic number. And again, period, time divided by 7, frequency, 7 divided by time. We're going to focus today on the repetitive motion of a pendulum. Pendulums swing back and forth like clockwork. Okay, we run across pendulums in a lot of strange places. They're not the most important thing we're studying this year, but they're important because they help set the foundation for more complicated motions. So we did a baseball in a pocket lab, and we watched the baseball as it oscillated back and forth, and we saw it got close, it got far, it got close, and when we plot this out, we get a repeating pattern, a repeating graph, position versus time. That graph will help us determine the period and frequency of the pendulum. Okay, so it's going to look something like this. You can see it live tracking as the ball gets close and as the ball goes far. Okay, and what we wanted to do from this lab was figure out what things mattered and what things did not. What factors affect the pendulum and which things are not important. Okay, so there's a lot of potential factors. The length of the pendulum, the mass of the pendulum bob, the angle that we pull it back to, the gravitational field of the planet we're working on, and if we give it a little push, or whether or not we just release it. It turns out that not all of these things matter, so we're going to group them into factors and non-factors. We did in lab period and length, and we saw that length was indeed one of the things that affected the period of the pendulum. We saw that as length got longer, the pendulum took longer to swing back and forth. We see that it's not proportional, so doubling the length does not double the period. It's a square root graph, so that means it takes 4 times the length to double the time it takes to swing. The graph has an equation that looks something like this. Period equals some number times the radical L. It turns out that this other number depends on some other factors that maybe we can or cannot control. All right, so let's take a look. Angle. When we do angle and period, we find no relationship. Why is that? That's because if we do a small angle, it's going to move slow but cover a really small distance. When I do a larger angle, it's going to move faster and cover a larger distance. Because of the fact that it speeds up at bigger angles, it actually cancels out. The extra speed and extra distance cancel out, and the time it takes to swing stays the same. This is approximately true for most angles, but if the angles get too extreme, this relationship can break down. But for all practical purposes, angle does not affect period. It turns out that the mass also does not affect the period. So long as it's heavy enough to overcome air resistance, all these objects will swing at the same rate. It's just like when we drop the objects. The heavier objects experience more force, but they're also harder to accelerate. It's the same thing with the pendulum. So the mass is a non-factor. The other thing that makes a difference is gravitational field. A stronger gravitational field is going to make the pendulum swing more rapidly. Okay, these all come together to give us an equation that looks like this. Period is equal to 2 pi square root of the quantity length divided by gravitational field. The length we want to use in meters, and on this planet we'd use a gravitational field of 9.8. Okay, so I'd like you to try using this equation to figure out how much frequency and how big of a period we would have 1 meter long pendulum. Realize when you're measuring pendulum, it's from the attachment point to the center of mass, not just the string. Not all the way to the bottom, but to the center of mass. Okay, so you start with your formula. Again, if you want to find frequency, once you get period, you do the reciprocal of it. You plug in 1. You evaluate the inside part of the square root first. You then take the square root of that number and multiply it by 2 pi. We get 2 James Bond seconds for the period. When we do the reciprocal of that, we get a frequency of around 0.5, about half an oscillation per second. Okay, so I'd like you to try this one on your own. This one we're going to try and work backwards. We've got Avery over here, and she's going to release the baseball and allow it to swing back and forth off the bleachers. And we're going to time it. And I'd like to see if we could figure out how high the bleachers are based on this swinging motion. Okay? So 2 swings take this long. So to find the period, take this, divide it by 2. Take that period, plug it in here, and solve for length. It's tricky, so be careful with your algebra. We'll go over something like this in a future day. I just wanted you to try it on your own first.